So on your worksheet, um, chemical kinetics, collision, and mechanisms, I'm going to do problem number 3 with you. This is one of our more complicated problems, and basically they give you a rate law that's determined from experimental data, and they want to know if it's consistent with the mechanism. So we need to write the rate law from the mechanism. Now, the first thing to notice is our slow rate is not the first step, which means it probably contains intermediates or catalysts, which cannot be in the equation. So I've boxed the intermediates. Here it's a product and then a reactant. It's also here, but it's still an intermediate, so it can't be in there. So I'm going to use my slow step to write my rate law. Rate equals K, IH, and I, okay? But these two are both intermediate, so I need to figure out what's going on here. So let's start with my I, okay? So I'm going to start with my I here because that's an easy one. Now, why is this called the steady state approximation? First of all, these guys are equilibrium signs, and equilibrium is when the forward rate equals the reverse rate, and when that happens, these concentrations stay constant. So that means that we have a steady state. That's why they call this steady state approximation. So right here, I can say that the rate forward, which is I, is going to equal the rate reverse, which this becomes the reactant then, and that's I squared. And remember, we can do that because that's an intermediate step. Now, most places you're going to see teachers putting in these K forward and K reverse. But what happens is you roll all these K's into a new K anyway, so I feel like they just muddy up the water. So I'm not putting in my K's there. They disappear anyways. And it's easier to see what's going on here. So to find I alone, I need to take the square root of both sides. And what I get is this I is going to equal the square root of I2, okay? And, that's usually a diatomic and it's not, so it's super unstable. Okay, so we have part of that. I can substitute wherever I have I can substitute in that. And now I need to find the IH2, okay? So that guy is here alone, so I'm going to use that one. Okay, you could use this one, but you'd be mixing things around and it would be a mess. So basically the rate forward is going to equal the rate reverse. And again, my K's are gone because they're all going to be rolled up into 1K anyways. So wherever I have this, I'm going to substitute in that. So let's rewrite this now. And I have rate equals, we're going to have our K, and that's going to have all the forward and reverse K's rolled into one. And here's my IH. So I'm going to substitute in this, right? So that's I H2, and then and then I have my I here, and my I is going to be the square root of I2. Now, this guy is an I, so I have to put in the square root of I2 there also, so okay. And I'm going to put them together. So I'm going to put my H2, and then my square root of I2, and I have another square root of I2, right? So my rate is going to equal all those forward and reverse K's rolled into one rate constant, H, and then I have two square roots, so that can be I2, okay? So now, this rate that I've just determined from the mechanism is the same as the rate from the experimental data, so we can say it is consistent. Okay.